Na plus K plus ATPase. This is our enzyme, which it is going to take 3 sodium ions that are currently inside of the cell, 2 potassium ions that are outside of the cell, an ATP, which happens to be inside but doesn't really, well, it's relevant, but it's not something that is pertinent to this particular case because we're moving sodium potassium ions in and out and everything like that. And our final product, or product if you want to call it a product, is we've got 3 sodium ions that are outside the cell, 2 potassium ions that are inside the cell, ADP and PI. Okay, now this is a good visual demonstration of what we're seeing. We've got our 3 sodium ions outside the cell, we have our enzyme Na plus K plus ATPase, we've got 2 potassium ions that are now inside of the cell, and we've got ATP and ADP and PI that have been produced. The water's not shown, but you can imagine that within the cell there is a cytosolic space that has water. Okay, so it's a soluble, or it is soluble, so you've got water in there. This maintains intracellular sodium low, or it maintains a low sodium ion concentration intracellular and a high potassium ion concentration. This is crucial for all organs, but especially for neural tissue and the brain. ATP hydrolysis, so that cleavage of ATP into ADP and PI, is what is essential for this actual driving. This is considered to be an antiporter because we've got molecules moving in opposite directions. There are 3 positive charges that move out for every 2 that move in. So our sodium and potassium ions are obviously different, especially whenever you consider like ion size and everything like that. But if you want to think about this simply in terms of their charges, we've got 3 positives going out, 2 positives coming in. Okay, all cells expend a large fraction of their ATP to maintain the cytosolic Na plus and K plus concentrations. Now, one thing that I always like to mention whenever I teach this and talk about this is that maintenance of these levels is absolutely important. So, you know, you're going to spend a huge amount of energy doing this, but think about like sodium ions and potassium ions that you bring in. Well, if you think back to Gen Chem 1, one of the first terms that you learn about when it comes to ions is electrolytes. Now, I always like to think about these because it's these sodium potassium pumps that or channels that are responsible for basically helping muscles continue to continue to contract, therefore your heart continue to beat and you to basically live at the end of the day. So I think that it's always worth mentioning these because if you think about like someone who unfortunately passes away in a marathon or an endurance event, chances are that it's probably because of a heart attack, and it is probably because of an imbalance of your sodium ions and potassium ions. Alright, so how does this function? So this is just another representation of that exact same enzyme, that exact same process. Now I want to go through all of these different things along the way. So what you have here is E1. That's this enzyme, or this first form of this enzyme. It binds 3 sodium ions. As soon as it binds 3 sodium ions, this is our starting point, what it's going to do is it's going to bind ATP with the help of magnesium. Magnesium is going to help stabilize 2 of those phosphate groups. That's going to give us this form of our enzyme that has 3 sodium ions, and 1 ATP molecule. Now what's going to happen here is temporarily this phosphate, one thing I got ahead of myself on was we are inside of the cell because we've got our sodium ions inside the cell that we want to get outside of the cell. Okay, so we're going to, inside the cell, bind ATP after we've already bound 3 sodium ions. Once that happens, we can take that ATP molecule and transfer one of those phosphates to an aspartic acid. We'll form an aspartyl phosphate residue. Now this is significant and noteworthy because we think about phosphorylated amino acids, but we rarely think about an aspartic acid as one of those phosphorylated amino acids. But in this case, we do have that. Generally, when we think about phosphorylated amino acids, we think about a serine or a threonine or something like that. So we have this E1 that has been phosphorylated, has 3 sodium ions. Now what's going to happen is this enzyme is going to undergo conformational change, in which case it's going to basically twist and move those sodium ions outside of the cell. Once it's outside the cell, it's going to release those sodium ions. So now we still have a phosphorylated enzyme, but now this enzyme, having undergone a conformational change, is known as E2. So the phosphorylated E2 is then able to pick up 2 potassium ions from outside of the cell. When it binds those 2 potassium ions, now we have E2, our different form of our enzyme, that is phosphorylated with 2 potassium ions. We're going to bring water in to release that phosphate from our aspartic acid, and now we've got our E2, our different form of our enzyme with 2 potassium ions bound to it. It's not phosphorylated. This will undergo a conformational change, which will yield the release of 2 potassium ions. Once it releases those 2 potassium ions, this enzyme that has undergone another conformational change is able to bind 3 sodium ions, and now it is the E1 or 3 Na pluses. So what I recommend whenever it comes to learning about this and studying this, you have to think of a starting place. You have to think of that starting place and what does it mean in terms of what can it bind. So if you think back to E1 versus E2, well, E1, that's the form of the enzyme that can bind 3 sodium ions. Only whenever it's bound those 3 sodium ions can it bind to ATP. So E1 alone, can that bind to ATP? No, it can't. It has to bind the 3 sodium ions, and then it can bind ATP. E2, on the other hand, well, is E2 alone ever going to exist anywhere? Well, no. Anytime we see E2, it's phosphorylated, or it's bound to 2 potassium ions. So a strict E2, that's not really going to exist anywhere. Okay. Now, ultimately, let me erase this. Here's kind of some summary notes about all this. The key to the sodium-potassium ATPase is the phosphorylation of a specific aspartic acid residue on the transport protein. ATP phosphorylates the transporter only in the presence of sodium. I said that just a moment ago, that E1 is only going to be phosphorylated or bind ATP whenever it is also bound to sodium. Now, this aspartyl phosphate residue is subject to hydrolysis only in the presence of potassium. So this phosphate group is only going to be removed when you have 2 potassium ions present. Now, so to sum that up and using some different terms there, E1 has a very low affinity for potassium, but a very high affinity for sodium. So E1 can take on those sodiums. That's not going to, you don't have to worry about any of this potassium that you've deposited. You don't have to worry about E1 picking that up and doing basically the same reaction backwards or anything like that. E2, on the other hand, is a very low affinity for sodium ions, but a very high affinity for potassium. So as soon as E2 releases these 3 sodium ions, well, now it's in a better position to bind to potassium. But like I said, E2 is phosphorylated, and only when it's phosphorylated will it actually bind to potassium ions.